In this video, we'll start with section 5.4, improper fractions and mixed numbers. So they looked at improper fractions before as copies of unit fractions. Okay? Now we want to connect that idea to mixed numbers. Okay? And again, they're usually pretty good about, well, at least writing mixed numbers as improper fractions, but we want them to be able to connect the representation of an improper fraction on the number line and with rectangles so they can have a more solid understanding of it. And it's really interesting some of the things they do with these. So for example, for 7/5 we have two rectangles. Notice again it says a single rectangle is a unit. And I always make the standard disclaimer, pretend that these pieces are of equal size. Okay? And if they represented 7/5, they'd likely, of course there's multiple ways to do this, but maybe they'd shade in 5 here and 7 here. Okay? So this would be 7/5 if one unit is the rectangle. You'll be surprised that when they go to write this as a mixed number, sometimes they start looking at the two rectangles as a unit, and they'll say that the mixed number is 7/10. Okay? Or vice versa, they might be fine with calling this 1 2/5. Okay? But then when they go to write this as an improper fraction, or if you just ask them to write this as a fraction, they say there's two rectangles and they'll make a denominator of 2. Okay. So these types of exercises really show you a lot of the things your students were probably thinking all along that you never noticed because we weren't asking the right questions. We were just going through and saying, hey, add them, subtract them, etc. Okay. So if we can get them to focus in on what the unit is and then see this as one whole unit plus 2/5, then they can write that as a mixed number. Similarly, on the number line, here we have -8/3. I'm going to put 0 here so I have enough room. Okay. You'll see in the Math AS problems also, these are partitioned already in the Math AS problems, but we only label the integer values because we want them to have that experience of counting 8 copies or -8 copies of 1/3. So notice they could start here at 0, and if they're cut into thirds, they can count them 1, 2, 3, 4, 5, 6, 7, 8 in the negative direction. Okay? And then they can begin to connect this idea. Well, we had two holes in the negative directions, or 2 1s, and then 2/3 here to get the mixed number value. Okay. Let's look at the next one. Okay, so next we have equivalent fractions. So let's look at some ways we can talk about these. So we start by giving them a fraction. Again, we try to use many different representations. Here's a circle, here's a rectangle. Okay. Here, one circle is a unit. We didn't actually say it in this case. Here, one rectangle is a unit. We're told that these are 2/3. And we're asking them to write equivalent fractions. So in general, we usually ask them to write equivalent fractions for one of two reasons. We want them to simplify a fractional answer, or we want them to build up a fraction so they can create common denominators. Okay? And to add or subtract fractions eventually. So here our goal is we really want them to understand that there's an equivalence class of fractions that equal 2/3. There's actually infinitely many of them, and the fraction 2/3 is going to be our simplest form. So we're not going to talk about officially simplifying and what that means till 5.6, but you get the idea. So here we want them to make equivalent fractions by cutting into more pieces. So if we have a circle and we have this is 2/3. We want them to cut into more pieces. Maybe they cut the thirds into 3 equal pieces. Okay. Now we see that there's no longer, well, you probably can't see it because this picture is bad, but there is now 9 pieces, and there are 6 of them are shaded. Okay. So we want them to be able to see this cutting, how it makes more pieces, which is counterintuitive sometimes, and then the corresponding amount of pieces shaded also increases along with the total number of pieces. Okay, so this idea, we cut everything into 3 pieces. We had 2/3, or each of the thirds into pieces. That made 9 pieces, and that turned the 2 pieces that were shaded, it also turned them into 3 times as many pieces, which is 6/9. Okay, so this is one direction. They're pretty good at this. The next direction is a little bit harder. Okay. So create 2 fractions equivalent to the given fraction by grouping the total number of pieces into a smaller number of equal pieces. Okay. So the problem here, or what they find difficult, and you can imagine this, is in real life when you cut something into pieces, you can't really uncut it. Yeah, you could glue it back together, okay? But when they see these lines drawn and things cut into pieces, they can't imagine that you could undo that cutting. Okay, so this would be simplifying, and I wish I could draw here, but I cannot. Notice that this is equivalent to 2/3, even though it doesn't necessarily look like it. I'm going to work with the circle here. Thankfully I worked at Pizza Hut, so I know how to cut something into 12 pieces. There we go. Okay. Now we have 8 of them shaded. Set the highlighter, 2, 3, 4, 5, 6, 7, 8. Okay. So now we want them to think of, they have to think of factors, and you want them to try this on their own and not necessarily tell them find a common factor between 8 and 12, but find a way to group these. So you want 2 things to happen. You don't want to have partial pieces at all, okay? And you also don't want the shaded ones to be partial. So notice I could break 12s into groups of 3, but then one of my groups of 3 would only have 2 out of 3 shaded. So I will break them into 2s. There's a 2, 2, 2, and 2. And usually this is a mess, and it's a good idea for them to rewrite it so they don't have to see the cut parts, because again they always want to uncut them. So, oh, that was terrible. So now here we go. So it kind of looks like this. Again, imagine they're the same size pieces, and now we have 1, 2, 3, 4 are shaded. Okay. So we want them to recognize this equivalent area. Okay. So it's, and you have them do that in 2 different ways, and notice on these ones, unlike those ones, I left or gave them blank ones to fill in to write their simplified version. Okay. Let's look at the next section. Oh, and then we have some examples where we give them different denominators and numerators and have them rewrite them in all different ways. And again, it's nice that we use this for simplifying and writing a least common denominator later, but we want to see them do this in general and let them know they can do this in general, and that all of these fractions are equivalent. Okay. And then we have 5.6, writing fractions in simplest form. Okay. And you probably know there's about 87 different ways we like to talk about something being in simplest form. So here, the simplest form of a fraction, or I should say the words we use, the simplest form of a fraction is the equivalent form of the fraction where the numerator and denominator are written as integers without any common factors besides 1. So what I meant by the 87 ways wasn't the simplest form, but we may say simplify the fraction, which probably isn't a good idea, because if you had 3/6, if you write 2/4, that is simplified, but we sometimes write that. or simplify your answer, but we probably should say simplify your answer completely. Okay, and there's other ways we talk about this too, so they have to be familiar with some of the expressions we use. Okay. And here, this example just helps them to see, which one do you think is most simple. The 1/2, 2/4, 3/6. I like to show them some maybe like 5,000 over 10,000. Okay. That's equal to 1/2, but that's probably more difficult to make meaning of in the 5,000 and 10,000 form. It's hard to visualize something broken into 10,000 pieces. If you have a true understanding of this, you're probably thinking of 1/2. So what does it mean to be simple? And then we look at 2 different ways of simplifying fraction: repeated division or prime factorization. So we wanted to have a couple of ways to do this because we always want the students to have multiple strategies. And the idea is, that prime factorization or finding the greatest common factor, we can create an algorithm that always works, okay? But sometimes it's just really unnecessary. So if you have 8/12, okay, one way you could do this is just, realize the greatest common factor is 4, okay? But maybe you just see that they're both even. You can probably imagine a student doing this. Divide by 2 once. They're still even. Divide by 2 again. And now we see 2 and 3 are both prime. Okay, so that's the idea with the repeated division method, is sometimes you just look for the factors you recognize, try to make them smaller, look for key things like even numbers or ending in 0 or 5. We didn't discuss the trick for 3 with the sum of the digits in Unit 4, but you could talk about that if you want. So this is one way. When worse comes to worse and when the numbers start to get big, so maybe with 84 and 63, okay, I can see that they're both divisible by 3. But this might be one it's a better idea to use prime factorization. I'm going to go with 4 and 21, 2 and 2, 3 and 7, 9 and 7, 3 and 3. Okay. So we'd have 2 times 2 times 3 times 7. Sorry, I'm running out of room. Over 3 times 3 times 7. Okay. And then you can show them the factors that cancel and say cancel to 1, or else they think it cancels to 0. And we're left with 4/3. Okay. So this method, the prime factorization method, is great because if you factor it into primes, it's completely simplified. You're definitely done. Once you realize there's no other common prime factors, there's not going to be one you miss. Okay, but then again, that in practice we might use this other method more frequently. Okay, we'll start on the next section in the next video.